Hello everyone. So we have completed the problems on single stage air compressor. Now we will go into the multi-stage air compressor processes. Okay. So what's the single stage air compressor problem so that you can get the idea how to solve the problems on the air compressors initially. Then you can understand the multi-stage air compression problems very easily. Okay. So now we shall try to solve very easiest problems in the initial, then let us go for the difficult problems later stages. Okay. So let us start with the problem. So the problem says a two-stage reciprocating air compressor. So it is a two-stage air compressor. Okay. Uh, Compressor works between the pressure limits of 1 bar and 8 bar. So your input pressure could be 1 bar and your output pressure from the compressor is 8 bar and draws in the air at 15 degrees Celsius. So the temperature of the inlet is also given. So at the rate of 467 liters per minute. So he has given in liters per minute. The volume flow rate is given in liters per minute. So you can convert it into meters cube, whatever units you have required. So the compression in both the stages is isentropic and the intercooling is perfect. If the intercooling is perfect, what happens? I have explained in the previous video, just refer it. Okay. Estimate the minimum work power supplied. So minimum work supplied he has asked. So what is the minimum work that you have to supply for this particular system which has been described just now. So for this you have a formula which is given as mass flow rate into the work input. So the work input is being calculated as this particular formula where it is N here and even N here, correct? The capital N. So capital N, the number of stages is 2, that's why it is replaced with 2 here. Okay, I have written the formula directly. So instead of N, it is 2 here and 2 here. Okay. Now, M is your mass flow rate. Okay. So just substitute all the things including M, you will get the values as 4.46426 kilowatts directly. Okay. So this is a small bit of problem. We shall try to solve another problem which says in a two-stage reciprocating air compressor with intercooling, that means it has an intercooler inbuilt, the pressure and temperature of the air are 1 bar and 37 degrees Celsius. What are these conditions? This is at the inlet of the thing. So at state 1, what is your pressure is? Pressure is 1 bar. What is your temperature? Temperature is 37 degrees Celsius. Now the delivery pressure is 12 bar. So delivery pressure in the sense it is this particular thing here. Okay. The pressure at which the delivery happens. So that is given as 12 bar. The intermediate pressure is at the optimal value. The sentence is so beautiful and important. Okay. So the intermediate pressure is at optimal level. So the value of Pi is optimal. So what do you mean by optimal Pi? The value of Pi at which the work input to the system is minimum. Okay. The value of Pi at which the work input to the system is minimum is known as the optimal value of Pi. And you have even derived the condition for the optimal values, optimal condition for the minimum work input at the last part of your theoretical part, is it? So that same condition you have to use in order to calculate your value of Pi. So how do you come to a conclusion that you have to use the same expression to calculate the value of Pi? Listening to this particular statement, the intermediate pressure is at the optimal level. Optimal level in the sense it is at the optimal level. You have to consider the optimal condition. Okay. Next we shall go further. It is given that this compressor saves 13% of work required by single stage compressor. So we have done a comparative problem also on this. So comparative problem in the sense comparing the process, the work done by a single stage compressor and comparing the work done with the two-stage compressor. So what is the percentage decrement in the work you have calculated in one of the problems? So kindly refer it in the previous videos. Okay. Work done with a single stage compressor between the same suction conditions and the same discharge pressure. Calculate the heat transfer per kg of air in the intercooler. Take the value of the polytropic index as 1.3 here stated in the problem. So let us go with the solution. So solution is given as the intermediate pressure for the optimal values, which I have just stated the condition. P2 could be equal to square root of P1 and P3. So that is equal to square root of P2. The P1 value was 1 and P3 value was 12. Just substitute it. You'll get it as Pi value to be, or P2 value to be 3.464 bar. So considering the polytropic process from 1 to 2, so 1 to 2 is which process? It is a polytropic process of index 1.3. Use the PVT conversion equation to know the value of T2. So this is the value of T2 here. So the T2 value was 418.96 Kelvin. Okay, just use the PVT conversion equation for a polytropic process. You know it very well. Since the process 1 to 3 is isothermal, okay, so this process 1 to 3, it could go in either of the ways. So T1 equal to T3, that is equals to 300 Kelvin. 310 Kelvin. Okay, so it is an isothermal process. Since it is an isothermal process, the heat rejected in the intercooler per air is given by Cp into T2 minus T3. So this is the heat rejected in intercooler, correct? I am marking with a red line here. So that is the intercooler part where your temperature would be reduced from T2 to T3. Okay, so that is why intercooler is there. So for that intercooler, heat rejected could be Cp into T2 minus T3. You have know the value of T3, you have calculated the value of T2, then this is the value of heat rejected in the intercooler. Okay. Try this problem if two-stage air compressor with complete intercooling delivers air at the mains at a pressure of 30 bar. So delivery pressure is how much here? It is 30 bar. The conditions are 1 bar and 15 degrees Celsius. So suction conditions, that means the input conditions are how much? The pressure is 1 bar and your temperature is 15 degrees Celsius. Do not forget to convert it into Kelvin. If the both cylinders have the same stroke, that means the stroke length of both the cylinders are same, find the ratio of cylinder diameters for the maximum efficiency. See, for the maximum efficiency in the sense, you have to use your optimal condition. So if you has mentioned for the maximum efficiency, you have to use for optimal condition. So what is your optimal condition? It is Pi is equals to P1 and P2. Okay, square root of P1 and P2. So index of the compression is 1.3. So that is all he says. Try this beautiful problem. If you have any doubt in it, contact me anytime. Okay.